Welcome to MIT InnoServe. This is our fourth colloquium, and this is launched actually 4 weeks ago. So we have been doing this weekly, but also based on the survey we did, we're going to change into bi-weekly. So the next one will be 2 weeks later. And I want to show the last time we did a survey on the topics people like to hear, interested in. And you can see they're very strong interest in new materials and with engineered properties, thermal properties. Lots of interest in whiskey and phase change, heat pumps. But overall, this is a range of topics. There are quite considerable interest on all of them. So we are going to reach out to community and find some of the people really expert in this area. We're going to organize the future colloquia first around these topics, and then we'll do more survey, and we are always open for input on future topics and suggestions for also speakers and topic as well as topics. And today, as we were just chatting, you already see we have a very international panel. The talk will be given by Professor Jiang from Tsinghua University on HVAC, and there will be very interesting debate on whether this is centralized or it's better to be centralized or decentralized. I'm sure we can learn a lot from today's discussion. And today's event will be moderated by Yang Zhu, Professor Yang Zhu, and I will briefly introduce her and then turn over to her to introduce our speaker and the panelist. But let me remind, the next event will be 2 weeks later, also same time, June 3rd. The talk will be by King Gusten on electronic cooling. And then we also have topic 2 weeks later on battery thermal management and safety. And with that, this is a slide introducing Yang Zhu, and she is currently assistant professor at the UC Santa Barbara. She got her PhD from MIT, and she also, very interesting, got her bachelor degree from Tsinghua University from same department as our speaker today, Professor Jiang. Her research is in heat and mass transfer, phase change, energy conversion and storage, thermal management of electronics, personal thermal management, micro nanotechnology, and thermal characterization. With that, I will turn to Yang, and Yang, you can take over from here. You can share your screen.
Thank you, Gang. Thank you. It's been a great honor for me to host this today's symposium, and I will share my screen with you. So it's my great honor not only to be part of this symposium, but to be really introducing our guest speaker today, Professor Jiang. He is currently a professor at the School of Architecture.
So Yang, you may want to use a full panel.
Yes, so I will try to share my whole screen. Yeah. So Professor Jiang, he's currently a professor in the School of Architecture in Tsinghua University in China. He's the director of Building Energy Research Center in Tsinghua University. So formally, he is the department in the faculty of Department of Thermal Engineering, Thermal Energy Engineering in Tsinghua University. So you will see in his talk that he has lots of experience in building energy efficiency, building thermal process simulation, and building automation, which is a class that I took in my undergrad. And he also has a lot of experience in building energy study and policy design. So he is a member of the Chinese Academy of Engineering and a member of the China's Climate Change Advisory Committee. So we also introduce today's panelist. So we're honored to have 3 members on our panel. So first, I'd like to introduce Dr. Ravi Prasher. Professor Ravi Prasher, he is currently the Associate Lab Director of the Energy Technology area in the Lawrence Berkeley National Lab. So he's also an adjunct professor at the UC Berkeley in the mechanical engineering. Previously, he was the vice president of both in industry as well as SheTech, as well as in ARPA-E as a program manager. You can see that he has managed programs related to building energy efficiency and high energy advanced thermal storage program. In addition, he's also was a technology development manager at Intel, and his research area is very broad, ranging from nanostructured materials to thermal devices. And our next panelist, we have Professor Alexis Abramson. She is the Dean and Professor of Engineering in Dartmouth College. Formerly, she is a Professor of Energy Innovation at Case Western Reserve University. She is a Chief Scientist, Manager of Energy Emerging Technologies Divisions in the U.S. Department of Energy's Building Technology Program. And she's also was a technical advisor for Breakthrough Energy Ventures. You can also see that her broad research interests are ranging from building energy efficiency, nanoscale energy transport, thermal electrical and thermal electronic properties of nanostructures, composite materials, biomaterials, interfacial thermal resistance, and computational modeling of heat and mass transfer. Our last panelist is Dr. Satish Kumar. He is currently a president and the executive director of the Alliance for an Energy Efficient Economy in India. And he was formerly the vice president and energy efficiency ambassador at energy management at the Schneider Electric India industry. So he's also formerly, he worked at the Lawrence Berkeley National Lab. And so with that, I would like to briefly introduce today's agenda. So we will have Professor Jiang Yi to share with us his talk on discussing building heating and cooling ventilation systems. His presentation will last for about 30 minutes. We will have 2 pop quizzes for the audience because the goal of this seminar is really to get feedback and promote discussion, promote communication with our community. And at the end of Professor Jiang Yi's talk, we will engage panel discussion. And well, you are welcome to submit your questions for the panelists through the Q&A button in the Zoom. So if you look at the bottom of the Zoom, you will see this Q&A function. So this is where you can type in your questions throughout, anytime throughout our seminar. We'd like to remind everybody that we may receive lots of questions and we may not be able to answer all of them, but we will choose questions based on popularity, and you are welcome to indicate your name and your affiliation. So by default, we will be reading out your name, we'll be announcing your name and affiliation. If you prefer to stay anonymous, please state so when you're submitting your question. And so I would like to quickly remind you that this symposium, this colloquium is being recorded as of now, and still will be recorded. The reason is that we would like to post-process them and post them onto the YouTube so that more audience could have access to today's talk. We will try to address additional questions that the panelists cannot address today, and we will try to include them into the recording. Last, just to briefly emphasize that if you prefer to stay anonymous, please state so in your questions. So with that, I would like to, first, before we introduce our speaker, I would like to launch 2 quizzes for you. And so, because today our topic is going to be on building energies. So let me try to stop share. We will try to focus on building energies. So we thought that it will maybe interesting for us to get some feedback on our general perception of building energies. So I will launch the first poll question. So I think that in your screen, you may see the number 1 kind of a quiz question. So the question is, which of the below should be prioritized when we operate an air conditioning system? Right, so the first is that we should be maximizing the efficiency of the equipment, including the chillers or the fans, etc. The second is that we should be focusing on reducing the total energy consumption, even though the equipment may not be operating at their maximum efficiency. And the third is that they're equal. So maximum efficiency means low energy consumption. And I think that we have increasing number of people answering the polls. So I'll leave it open for another few seconds before we end the poll. So again, the question is, when we're building air conditioning systems, which should we prioritize? Should we prioritize maximum efficiency of the hardwares, or should we prioritize over reducing the total energy consumption? So I think that I would like to end the poll here and show the result. So you can see that most of us thinks that reducing the total energy consumption is more important. And you will see through Professor Jiang Yi's talk is that this is indeed, this should be prioritized over in focusing on individual efficiencies of the equipment. So the second quiz will be that, I think that I have just launched the second quiz. This question asks how much energy saving can be achieved in an intelligent building, which is one that with analytics and advanced controls. So how much energy savings in terms of percentage can be achieved if we have intelligent building? Just guess a number. So I think that as people are entering the answers, we like to mention that an intelligent building and in the future maybe an interesting future direction, also buildings with artificial intelligence. So hopefully you can also see this through Professor Jiang Yi's talk. So now I think that we have got a lot of response. So you can see that a lot of people guessed between 30 and 40%. And this is also very Very great answer. So now I would like to stop, share the result. And I would like to, we finished the 2 quizzes, and hopefully you find, building energy, it's really related to our daily life. And I would like to now, give the stage to Professor Jiang Yi, and he will, he will share his screen and start his presentation. So Professor Jiang Yi, if you could share your screen with us, please go ahead. Thank you.
So then can you switch off this? Okay, fine, thank you. Thank you, Yang Chen, for your introduction. Thank you, Professor Gang Chen, to invite me to give this talk. And good morning, good evening, good everyone. And the topic I'm going to talk today is something like a centralized or decentralized of the building service system, especially HMAS system. And because the building energy is really something important. Okay, and by the years of 2018, the total the building energy use in the world is take almost 30% of the total energy of the world, and the carbon emission is also as much as 28%. And here is still big difference between the developed countries and the emerging countries. If you see the left corner, here show you the building energy used in terms of the per head. This is the horizontal, and the vertical is in terms of the per square meters of the building floor area. You can see there are really big difference. And on the right side is show you the CO2 emission in terms of per head. Also, different countries are seems quite different. Where the red was the building responsible for the CO2 emission. Why there's so huge difference? One of the reasons is a different type of the HMAS system. So then we go to today's topic, the centralized system or decentralized. Question one, in terms of the energy used, well, what's different? And the meaning I said centralized system just like this. You have, for instance, you have the central chiller here, then you have the chilled water distribution to deliver the chilled water to each 100 unit, where you make cold air to go to everywhere, to go to the VV box, and then they deliver the cold air to each space. This is the central air conditioning system. For the decentralized means every room, maybe you have your own split unit, you have indoor unit and outdoor unit, and they can do independently. And now let's see some real data. Here is measured data. We take this ABC 3 residential buildings in Beijing, and each room, every room in these 3 buildings do have air conditioning for the summer for cooling, but the electricity used in terms of per square meters, all of the summer, you can see is relatively low, only 2 or 3 kilowatt hours per square meters. Then you come to building D, it's something like a small scale of central air conditioning. They use so-called VRF multi-indoor unit connected with one outdoor unit. The energy used a little bit higher is 5 kilowatt hour per square meters annually. But then you come to the building E, is a big also for residential apartment. They have central air conditioning system for 24 hours served. And the electricity they used is almost 20 kilowatt hour. It's almost 10 times as this A, B, and C. Why? What the difference? Is in fact it's quite simple because the building E is a central air conditioning system. They provide service for 24 hours a day and for every space. But the ABC like this is decentralized. Every room they have one, and then people, when they empty the room, they switch off. That's only the difference. And then you can see here is one of the building, 25 families here. Then they give the data for cooling, also in terms of per square meters kilowatt hour. You can see huge difference. Means every family, also the building is the same, but every family is they run the air conditioner in a very, very different way. Then if you do the central system, you need all this energy. Then you can know where the difference come from. Okay, now let's go to the, then we said that's the low energy due to the part-time, part-space service rather than full-time and full-space service. And we did a very large-scale monitor on 200,000 VRF system like this. One outdoor unit then can be connected with 5 or 6 indoor units for whole family. It's in fact it's kind of central, small-scale central air conditioning. It's very modern in China here. And then we got the whole year's data, minutes by minutes, lot of few T data, huge. And then what we discovered, we found almost 60% of the operation time, the indoor unit, only one indoor unit turn on. Then another 27% of the time, they run 2 indoor units. Also, the system make 5 or 6 indoor units connected, but they only run 1 or 2. This is how they switch on. Then if you see the load, more than 40% of the time, they work, the whole system working under 20% of the load. And more than 70% of the operation time, the total load is less than 40%. It means they always working at part load. Only very few, almost very few times they can work in full load. This is really what the people was like in residential buildings. Then we make some large scale of the view to see different situation, how much the electricity used for cooling, and for the all use stability unit, you can see whatever they are Kangtong near Hong Kong, very hot place. Here is Beijing or different cities. Also, Wuhan should be here. Okay. Whatever the climate, the electricity used for cooling, if you still take per square meters of the floor, it's just around 5 kilowatt hour for years. But if you use Funko unit here, these 3 means you have central chilled water circulated, and each space they have individual Funko unit can turn on or turn off. Then the electricity used come to around 10 kilowatt hour or more. Then if you go to the really fully centralized system, like with radiation cooling on the ceiling, then the electricity used can be as high as 20 or more. So you see huge difference between the centralized, some centralized, half centralized, or independent decentralized system. Then we come to the large office building like this, downside you can see, and this case, they have mainly two types of air conditioning. One is Funcal unit, is the air system is independent space by space, but water system is connected big chiller water system. Another type is VAV system, is fully aired centralized system. You can see in Beijing, for instance, Funcal unit around 15 kilowatt-hour per square meters annually, but the VAV system fully centralized is more than 30 kilowatt-hour. It's quite a big difference. Then come to Shanghai, the Funcal unit similar, but then the VAV system you can say much higher. Why? Then we come to the US. I also got a lot of data from some city in US. Here is the data in Philadelphia, university campus in Philadelphia. You can see the office building A, B, C, D use VAV system for 24 hours operation. The annual energy electricity used is almost, you see, 200 kilowatt-hour. But very lucky, in the same campus, there's a building with the same function, office building, but installed with Funcal unit. You can see the total electricity used for cooling just around 30 kilowatt-hour. It's huge difference. So same feature combined with China, similar feature. Then we come to Japan, they have the large district cooling system, not a single building, but a number of buildings. Here is the Japanese District Cooling and Heating Association gave the data. They have more than 100 projects. Each one is one node here. And the base one, the Japanese believe is Harumi one is here. The COP is something 1.2, where they count the COP by the output of the cooling divided by the primary energy. But in US and in China, we used to use electricity. Then you have to, according to Japanese situation, you have to multiply that data by 2.6. Then you got 3.13. 3.13. That's the maximum one, the highest one of the COP. But what happened in US or in China, if you take a single building, big chiller on the ground, you measure the COP, normally it's 3 or 4. Even I found some building 4.5, that's very normal. But for district cooling, the COP, you can see from this curve, highest 3.3, lot of things below 3. That means the district cooling is not advantage combined with individual chilled system for each building. Okay, why? All this data from the residential building to large scale of the district cooling, always something, it seems to me, for the centralized is more energy needed, and for decentralized, less energy. Why? What reason? The people who support the centralized system, they believe they are the larger system, they are higher efficiency, and maybe by coincidence, they can less capacity needed, and then better operation, better management, even save space. But for the people who support the decentralized system, they believe for the small one, independent one, they are easy to adjust it and flexible for response. And also no energy need for distribution. That's also an advantage. Then for the part load situation, maybe they can got high efficiency. So two different points. Then where the central system idea come from, I believe they are come from industry. Because for industry, when you produce things, the larger the amount, the high efficiency you can got. However, there are something different. For industry process, the target is to produce things. But for building service, the target is to provide the service to the customer, to each occupant, and they produce for the industry, the product is always the same. The large amount of things exactly the same, they multiply to produce. But for the building service, also is for each occupants. But people by one by another, they always have different demand, different situation. So then, because the difference, that's the big difference. The demand is different combined with the industry process, same amount of large scale of the production. So then you can find maybe because this reason, the centralized large amount of things maybe not efficiency, maybe use more energy. So then the problem comes from the different on the demand. If central system, then we maybe think how to describe this different demand phenomena or the characters. So then we have to find some feature. What the demand feature? First, when you need to do something, need demand, okay, demand, then the system have to supply something. What is the relationship for building service situation? As soon as the supply larger than a demand in a certain range, then the people is satisfied. Means they are not asking you to equal, make the supply equal to the demand. But then for central system, because the demand is different one by another, then in many cases, the supply just meet the one who have the maximum demand. Then the rest of the terminal, rest of the people, they say, okay, I'm also satisfied, but in fact, they are oversupply. That's one case. Then you see the system, the building you need something, then the air system provide more, then the water system provide to the air, also add some more things, then the chiller add more. So by the end, the supply is quite higher than the real demand. So then we see another feature is the un-synch occupancy time. Means if you have a centralized system provide the service to a large number of the space, then you can find each space the time that they need to have the service are really something different. One space by another. Here is something in different city. We did measurement on the residential buildings for each space, when the people occupied and when the people living. They are very different on the time. So then, however, for central system, they have to run the service for all the space to meet the demand. Even if there's some empty room, they still provide service, also makes the oversupply. Then we see the quantity of the variation also is un-synch. But normally we're talking about heating and cooling. In fact, heating is something different from cooling. When you do the heating, the major influence factor for the load is the climate, is the temperature difference between indoor and outdoor. That's the major influencing factors. Because we are also building under single one umbrella. So then the temperature difference between indoor and outdoor is simultaneously variation. So then it's not so many problems. However, when you're talking about the cooling, the things getting completely different because the indoor temperature and outdoor, the difference is relatively small. And the major influence is the indoor heat gain, like solar, number of people, lighting, equipment, all these kind of things that makes the load change greatly during the day, and they are changed according to the real usage of each space. then because each space being used in a very different way, then the need for the cooling are very different like this. For different rooms, you can say really something different. So different time, different quantity. Then we say the quality also un-synch. Here is, for instance, for the VV system, because you need outdoor air to maintain your indoor air quality. So according to the number of the people inside, maybe one room you need 50% of the outdoor air, another room you need 30%, then another room you need 90%. Then for VV system, they can only deliver single kind of air to each room. Then they have to choose the maximum 90%. So they have to take 90% of the air is from outdoor, make high energy use. Or another word, oversupply for quality. Here is another, is the chilled water. We take that not only for temperature control, but also for humidity control. But normally, if you take sensate heat, you need, as soon as the water temperature comes to 16 degrees C, is good enough. However, if you do the dehumidification, you need 7 degrees C chilled water. So also the dehumidification maybe only take 30% of the total cooling load, but you have to make all the cooling load provided under 7 degrees C chilled water. You know, 7 degrees C water is much expensive compared with 16. You oversupply the quality of the service. So whatever time, the quality, everything, because the centralized, you have to always find the maximum demand, maximum requirement. You make this meet this demand, and then you supply to the rest like this banquet, like this banquet. Okay, now, then if you find really the un-synch demand characters is something influence the centralized system, then when we're going to study that, we do need a way to describe these characters, how un-synch of the demand. Then we can find, if you take this horizontal is the cumulated of the share of the demand, and then the vertical is the dimensionalized of the demand. You can find the requirement or demand distribution like this curve. Then that's the Lorentz curve. Then you can take this R divided by the triangle, you make the Gini index. Okay. This Gini index, that can describe how different the demand is, how un-synchronized change variated of the demand. So, for instance, for heating, if you're in Harbin in China, the outdoor temperature is -26, then in this case situation, the demand is very uniform distribution. Then the Gini index is 0.3. If you come to Beijing, -9, the Gini index is 0.5. It's still not too bad. But if you come to Shanghai, the outdoor temperature is 10 degrees C, you can find the distribution is really something ununiform. So then the Gini index is very high, 0.8. So they can show you how big difference, how unsatured of the load or the demand. And here is for large CBD area. If there's 80 office buildings plus another 10 hotel buildings with 2 bars, you can find each type of building, the feature during the day is something different. And then in the middle day, in the noontime, 11 o'clock, the Gini number is quite small because every building do need cooling. but during the night, this very uniform distribution, the Gini number come to 0.9, maybe only 2 bomb operation, and all the rest they switch off. So this can be described that as the parameters to say how the variation, how not a simultaneous change. Then we said we can study these 3 questions. First, what really the people need? And here we take more than 2,000 situation collected through our monitor system. We find the set point temperature. Normally people say, okay, I need 22 degrees Celsius, 24. And in the same time, in the summer, what happened? The set point the people need is from 16 degrees C to 30 degrees C in a very, very large range of the distribution. This comes from 2,000 cities. Then we got another 3 cities, Chongqing, Wuhan, Shanghai. All each city take more than 500 data. You see also in the summer, large range of the distribution, in the winter also quite different. Means there's not certainly small range of the demand. Everyone think, oh, what is set point of temperature? Even some people, they don't understand what means the set point. Then if there are central system, say VAV system, some people need 26 degrees C, some people need 20, and there's one people need 16 degrees C, very low temperature. What happened? The system has to try to meet this demand of 16 degrees C and to make this supply temperature, and then the rest of the room, rest of the space will be have to make some adjustment or in trouble. That's the demand. Then in this situation, can the system meet the demand? You see, we're talking about a different time. What happened if every space need be served at a different time? Then the central system has to operate it, even if there's only single space need to provide service. They still have to turn on the whole system. Then for VV system, for instance, because there's only one air handling to serve with 20 or 30 rooms, then they have to run that. Even only one room is occupied. Then you have the central chilled water system, even very small portion of the load or terminal that they need chilled water, you have to run the whole network. Then you see the outdoor air system. Normally, whatever in US or in China or in the world, for the outdoor air system, for central air conditioning system, they always full load operation, regardless how many people inside been take this service. Then the result is what happened. Because normally the occupancy rate of the buildings is as small as 20 to 40%. Then the central system just provide service for the empty room in most of the time. But for the decentralized system, they can provide service just to the space that is occupied and switch off the others. That's much different. Then when the need for cooling or heating amount is different, what happens? For VV system, they can change the volume to each space. They say, okay, I can do the adjustment. However, for small range, yes, you can, but for the large range, they can hardly do meet all the demand. Especially when everyone have different temperature set point, then this be very hard to meet each demand only by variation of the air volume. Then what happened? They have to use reheat. What means reheat? You see this curve. The outdoor air temperature, this, and the return water wet temperature 22, then mix it into 21, then they be cooled down to 14, and then before they are delivered to the room, they been reheat at the terminal back to about 20, 21 degrees C. So you use more than 200 kilowatt cooling, then you use 220 kilowatt heating. In the total, in fact, you only need 30 something kilowatt for cooling. That's good enough. However, in fact, they consume 500 kilowatt. This is the real data I got from one of the operation project in US, the real things. And here I show you 4 buildings also this annual data. Here is 4 different buildings located in Philadelphia, and horizontal is the outdoor temperature. You can see in the summer 94 degrees, in the winter 44 degrees, and the vertical is the BTU, how much heating and how much cooling they use under one temperature. For instance, outdoor temperature 70, then you sometimes different time you need this heating and you need this cooling. Then you can find whatever outdoor hot in the summer, they still need heating. You see, need heating, very hot. Need heating, even outdoor is 94 degrees. Then in the winter, very cold, they still need cooling, you can see. So at least 30% of the heating and cooling just be offset against each other, be lost, not being really used to the building. That's also one of the reasons is centralized system to do that. And then with the Gini index, we just mentioned, the more the ununiformed, the more high rate of the reheat. But if you cannot change the volume, then 55, okay, then be more reheat you need. You can find if they are very uniform, the small Gini index means all the space are simultaneously changed, then will be no need for reheat. That's the situation. So then we see the transportation system, how they make the adjustment on the water, on the air to meet each demand. First, for instance, we can say like the domestic hot water system, because people need hot water different time, but to make sure when they turn on is really got hot water, they have to make the hot water circulated 24 hours all the time. Even this less 10% of terminal need water, they still need to do the circulation. Then we find maybe half of the heat not being used for the terminal, but just be lost during the circulation. It's hot water. Then the VV system I just mentioned, the change the air volume cannot be completely switched off for the unoccupied room, so they also provide some service. Then the Funcal unit, they need chilled water circulation. Even there's only 1% of the people or the terminal needs the water, they have to make the whole water circulated all the time, and then outdoor air also the problem. So through the adjustment, it's hard to solve this distribution network, so makes the oversupply is the result. Then we see during the control in the network, if every air handler unit need different water flow rate, then you have to use the valve to control. What the function of the valve? Just to consume the pump's energy. The delta P who provided this delta P is the pump. So, and then you can find the more the ununiformed, the larger Gini index, then the more energy being used, consumed by the pump, by the valves, that's lost of the pump's energy. Not only the pump's energy, also because there, okay, here, there are some different water temperature from the each 100 unit because the load is different. Then they have the water mixing different temperature and make large amount of entrance dissipation here. And also if you even with 3 valves, here is some mixture temperature, different temperature with water mixture together also take a lot of entrance loss, all related with Gini index. Here is the equivalent temperature difference or entrance loss. So means also, yes, the transportation system can make the adjustment in most of the case, but it's just to try to consume the additional part rather than save something. They just try to consume the more part to make the measure, to make the control. Then I show you a very strange case study happened in China. There's a project in Henan. It's a water heat pump system to provide chilled water for cooling of all these residential buildings. There's about 500 units of Funko unit connected with this system. And the measurement we find in terms of per square meter of the building, the whole year, whole summer, the chiller electricity used is 4.4 kilowatt hour, not very large. But then the pumps consume almost similar. Then the cold, the produce cold water, chilled water, they produce cooling. The cooling is only 9 kilowatt hour per square meters. Then you take 9 divided by the energy, you got the COP is just 1.2. That's too small. Normally with this system we can do 3 or 4. That's the minimum. But in this case, only 1.2. Why something like that? Because then we made the measurement, we find the mean open rate for the Funko unit is only 7%. Means the people not always turn on. The most of the time they switch off the fan to save energy. When they're not in the room, they switch off. This is a Chinese habit. So then, but the water goes through circulated, so the pumps consume huge energy. The temperature difference between inlet and outlet of the chilled water is very small, less than 1 Kelvin. Then we did some simulation. We designed 3 models to use. One is just what happened there. When the people turn on the Funko unit is dependent on the indoor temperature. The mean value is 29, but it's the probability is a distribution. And when the people turn off the Funko unit, also dependent on the temperature, also a probability distribution. And then the set point is around 27 degrees C. Is one model. Another model is as soon as you're at home, you turn on, and when you leave in unoccupied, you switch off. That's another case. Then the case 3, the model 3 is whatever all the summer I always turn on, whatever I'm there or not, but also take the set point as 24 degrees C. Then we make 3 cases. One is most of the people is model A, another is most of the people model B, and some are A and C, and the third model case is most of the people working like C. Then it seems very interesting. The result is you can see the Gini index for this very safe energy model. They are very large, means sometimes this room turn on, sometimes another room turn on. It's very uncentered. But for the model, the case 3, it means all the time most of the people turn on, so it's very uniform. But the Gini index is very small. Then for this 3 situation, for the safety, you can see the COP is low, not good. efficiency law for all the used all the time. The COP is not too bad for, but the unused also very high. This the blue bar is the all the time operation. This blue bar is part-time, part space, and even when the temperature come to 27, 28, people forgot to turn on, they still switch off. So then the red bar is when you use the split unit. Suppose the split unit, the COP is only 3, and the blue one is a centralized system. The COP, the chiller COP is high, but when the people all use in the same time during the whole summer operation, then the centralized system use less energy, high COP, okay, high COP, less energy. And the split unit, the decentralized, they need more energy. However, for the safe model, the decentralized, less energy. The centralized in more. You can see we cannot certainly say always something. It's very, very dependent on the real usage model. So then we have to balance between the efficiency and the real consumption. The centralized and decentralized, not two opposite states, but continual process. What we study is try to make the balance between the supply and the demand. So then the discussion is we need high efficiency or the less energy used. The energy real use equal to the service demand divided by the efficiency. So high efficiency, you can use less energy. But for the service demand is include part. The effective demand means really useful, and the non-effective demand means for you give the service to an empty room, no people inside, it's just waste. So we need a high efficiency and we need less portion of this non-effective demand. A central system often causes oversupply, so to make large portion of non-effective demand. So if a high efficiency system leads to large portion of the non-effective demand, then maybe we prefer the low efficiency with low portion of the non-effective demand, so to reduce low energy. That's the key point. Okay. Then the people say the management and the cost we can find for the decentralized system device because they can at a very large scale produce, so they can be very low cost compared with large equipment centralized system. And then for management, as soon as the IT technology are well developed, they can be made. It's possible to maintain the decentralized system device with very high level reliability. So this will be not the point. Then the space also, as soon as the little really decentralized, then by the end you can save some space. So now we come to the conclusion. I think my time is run out. The building service is not the same with the industry process, is not the same due to the uncentralized feature. And then the central system may use more energy. And uncentralized operation time, load, and quality, all these kind of things lead oversupply with when you use the central system. Then the larger the number of the terminals, then the more uncentralized, then you got larger Gini index, then at the end is more energy use. So what we should do is to try to developing a decentralized system, improve the efficiency of the equipment, improve the operation with maybe AI technology, and improve the maintenance ability, so that this maybe should be the direction of the future development. I think. Thank you very much. That's my talk. I can switch off.
Thank you so much. Thank you so much, Yi, for your really, really inspiring talk. And right now, if I could ask all the panelists to gather here, I think that this is time for some discussion, and we have received a lot of questions from the audience. So what we are going to do is that we are going to select a few representative questions from the audience, and for the panels to share their own views. So first of all, I think that maybe I will ask all our panelists to, comment, say a few sentences or say a few things about, maybe introducing yourself or, your thoughts after Professor Jiang Yi's talk.
Right.
Okay, so I'm just gonna go first. Thoughts. First of all, very good talk. I mean, a lot of things, a lot of people have talked about distributed versus centralized. I just want to say that this is a much broader topic now, because it's not only energy use, you also have very high global warming potential of the refrigerants being used in this air conditioning systems. So I think the question I have is that how much is the leakage of refrigerant coming from, let's say, let's do a hypothetical study. Everybody has a central distributed air conditioner versus buildings have centralized. How much extra global warming refrigerant leakage will happen, because you have so many of these now. And as we know, that's one of the biggest challenges. So it's not only about energy, CO2 from energy, because maybe energy will become more decarbonized because of renewable penetration, renewable energy. So that is one thing that has to really take into consideration before people, as a society, we say, oh, distributed is the best way to go. Okay, that's one. Second is how much it will be the embedded energy, right? If you imagine that we keep on making so many of distributed air conditioners, there's going to be impact of materials supply, as well as an amount of energy needed to make those distributed air conditioner or cooling devices. And finally, in context of significant penetration of renewable energy, again, you have to really balance between which systems provide you more control and which systems provide you more demand response flexibility. So these things have to be taken into consideration, and from a very holistic point of view, and saying which system and which architecture is better. I mean, those are my overall comments.
Okay, thank you very much. Can I answer the question? Yang, yeah, you got a very important point about the leakage of the refrigerant. If you're talking about, say, 10 or 20 years ago, the leakage really some big problem. That's why at that time, I understand there is a special service that they take this refrigerant to go to every home to recharge that, because there's a leakage problem. However, now, after 20 years, now, we did a lot of survey to see what happened. Now, we find because the quality is getting better, so most of the air conditioner, especially for residential buildings, the split in unit, even after 10 years, not any leak. After this since been finished life, they still no need for recharge again. This for split unit, the decentralized. However, if you go back to the large chillers on the big building, what happened? Normally every year they have to do 1 time of the maintenance. If you will manage that, you can very good control to say don't make leakage or take the refrigerant away somewhere, then you handle that. However, in some cases, during the maintenance, you just open the system and take this refrigerant away. So my point in this, I did some special study, take some students, do some real investigation. We find now, if you say the quality of the system now, the decentralized split unit maybe deliver a leak less refrigerant compared with the big chillers. That's my point. Maybe someone have different option. That's the fourth. Second, you're talking about the manufacturing process, the energy used. I think the large system and the small system, they are not very different, because for the large system, maybe the chillers less, but you need piping system, you need data, you need all these things is also something. So in terms of the embedded energy, I don't think there can be big difference, but we need to do some more study to see that. And then the third question, if you say, if I heard correctly, is about the control. Can we solve this centralized system by good control? Yeah, a lot of people believe that, but I try. In fact, as Jiang said, I'm the control people. In fact, for many, many years, I tried that very hard. Say 20 or 30 years ago, when I choose control, I think maybe by good control, we can solve this problem. But now I lose my evidence. I think maybe that's quite hard. Instead of only do the control itself, maybe you have to do something at the beginning for the system, make the system more suitable for the real demand. Then is the total final solution. Thank you. I don't know the answer. Maybe you're happy. Okay. Yes. Satish.
Okay, I'll go. I know that I think we are probably running a little late. I have, again, 3 points to make based on the excellent presentation that was made. And I am Satish Kumar. I am based in New Delhi. So I will bring in some perspectives from India, where it is forecast that the biggest cooling demand for the next 20-30 years is going to emerge out of India because of a large population, very low penetration of air conditioner, both in residential building and in commercial building, and people's desire to own air conditioners as the middle class grows in India. So 3 things that I want to highlight, and then I would also talk about some other technologies that are not mainstream right now, which are being tried under the global cooling prize. So the 3 questions are that, is there one temperature set point? Professor Yi talked about it, that we should design it. And we know that ASHRAE has changed its comfort temperature definition. And what we are seeing is that the temperature set point that is going to be preferred by people in Scandinavia is going to be very, very different from somebody in New Delhi. And that could be a difference of like 6-7 degrees Celsius, about 10-12 degrees Fahrenheit. That can have a very, very significant impact. And what kind of systems, whether it's centralized systems, decentralized system, whether it's evaporative cooling, whether it's vapor compression, our technology system is going to be better geared for taking those things into account. So that's my first question. The second observation that I want to make, and this goes back to the point that Professor Yi made, is that you need to have controls where the latency in the system is fairly low. And by that, what I mean that you can change the temperature quickly, you can shut down the temperature, shut down the system without having negative impacts on the system. And the reason I'm saying that this is really important in the Indian context is because in India, the amount of air conditioning demand that is going to come out from residential system is about 10x than what is going to come from commercial systems. And I think that is something that needs to be kept in mind as we think for the next generation solution. The third point that I just want to make is, what about hybrid solutions? Right now, I think vapor compression technology is the way to go. But if we think about designing for passive solar design, if we design very good building envelope, try to reduce cooling demand, expand the thermal comfort envelope based on adaptive thermal comfort standards, then evaporative cooling, whether it's direct evaporative cooling or indirect evaporative cooling, can start to play a significant role. And this is what we have observed in the global cooling prize, that Rocky Mountain Institute, along with Department of Science and Technology, IEEE, CEPT University, and Conservation X Labs, is launched to come out with the next generation of solutions, where most of the big companies, including like Gree, Daikin, Godrej, from around the world, they are proposing hybrid solutions so that when the humidity is low, they can run it as evaporative cooler, and when the humidity gets high, they can actually turn on the vapor compression systems. And of course, there are some solid state cooling technology that has also come out. So I will stop here. I'm not expecting an answer, but I just wanted to put some of these things in context in terms of how India is looking to solve its cooling problem and what can be some of the technological fixes there.
Thank you very much. Maybe I also explain some of my ideas to answer your nice questions. First, about the setting temperature. What we believe, also different places, people, first, the different set point can make huge difference in real energy used. Secondly, what I believe is most of the people, they don't understand what temperature is more comfortable. They are not professional people, normal people, they do not. So then, even some people believe the set point means what temperature of the supply air you need. That's why they take 16 degrees C rather than 20 something. And then what we did for the centralized system, instead of asking the people to put your set point of the temperature, we just give the button, like people to comply. They feel too hot, you press this button. You feel too cold, you press another button. Then the system just learning according to the number of comply times. Then after a period of the days, few days, the number of the comply getting smaller. The system can learn how much you really want. Never let you to ask the temperature, just ask you to comply, and then the target is try to reduce the number of comply. This may be worse. This is the first answer. And then for the evaporative cooling, I'm really fully support you. The evaporative cooling is a very important techniques in the future to reduce cooling energy and to save our climate. And we just set up a big project, international collaboration under IEA, EBC. There's 6 countries, I believe, involved in this evaporative cooling project. But what I would like to say here is, for the good evaporative cooling system, not small device, big one, they only suitable for some large commercial buildings that they have to use a centralized system, or big hotel, shopping mall, this kind of thing. For residential, even the evaporative cooling system is very high efficiency, but because it's centralized, you need transportation, you need all this kind of stuff. Then by the end, you can find only the pumps, the fans, even this energy can be higher than if you put in decentralized small split unit. The small split unit still safe that. It means just as what I mentioned, you have the high efficiency. The evaporative cooling is high efficiency, but has to be centralized according to the feature. And then the decentralized, the small split unit is relatively low efficiency, but because it's small, easy to control. Then by the end, if you combine these 2 solutions, you can find for residential buildings, still split unit, the decentralized system may be better than the large evaporative cooling system. That comes from my practical situation, some survey and something like that. But thank you for your mention the evaporative cooling technology. That's really very important. Thank you. So.
I can jump in for a second too. Dr. Jiang, thank you for your great presentation and for challenging the status quo. I think when we think about buildings and we haven't seen as much innovation in buildings and about how to do things differently in the last few decades. And so it's really great to see that you're providing some information to us to sort of challenge that how we're thinking about buildings could be wrong in some cases. So I really appreciate that. I'm Alexis Abramson. I'm the Dean of Engineering at Dartmouth, and I've been working in buildings for a while. I want to just make a few sort of comments. One was with respect to your comments at the end in response to Ravi around that idea around intelligence and controls. And I think, you know, in many cases, you want to look at the individual case, you want to look at the building, and you want to understand, could you maybe solve this problem better with respect to putting a centralized system in and putting in some kind of intelligence and controls, right? I don't know. Some cases it might be better to some of the data you showed too. And I think it's important that we have the ability to do that analysis. And I'm not sure we do just yet, and how we take advantage of data analytics and machine learning better. And I think that's a really emerging field, and we'll see how that evolves. We need the participation of people on this, participants on this webinar too, to see how that evolves. So I think that's a really important piece of this. And I also wanted to mention on some things that were touched on, mention some things that were touched on too, and that, right, this is a complex picture. It depends on the country you're in, the economic structure of the country. It depends on climate. Certainly some climates are going to be better suited for a centralized system, some better suited for a decentralized system. Are we talking about an urban solution or a rural, building? And so all of that matters as well. And then policy, what kind of policies exist in the countries that are looking at efficiencies and efficiency minimums and requirements around efficiency of HVAC? And that's highly variable too, and that could also influence this. Also, what is the building's end use, right? Is it a coffee shop or is it an office building, right? And, very different kinds of energy use patterns in those building types. Again, that could influence the best solution here. And then I just wanted to mention too, let's not forget building envelope, right? Because at the end of the day, the better the building envelope, the less energy is consumed in heating and cooling, certainly. And so, so there's still a lot of innovation and market deployment of great building envelope solutions that need to be out there in the world so that we can further minimize our HVAC usage.
Okay, thank you very much for your point. But firstly, when you're talking about control, what means control?
If I don't mind, we are running out of time. Can we give it to the audience? We have only 10 minutes left.
Okay, sure.
So if you don't mind, Yang, this is really important that the audience get a chance to ask the question to the panelists.
Yes, thank you, Ravi, and thank you, Yi, for the wonderful discussions. So given that we only have 10 more minutes left, so I will, based on popularity, I picked 2 questions. So the first question is coming from Professor Leon Glicksman at MIT. And his question is on how about what's the role of natural ventilation and in the AC energy consumption? And another question, similar question, also coming from Amr Roth, also on natural ventilation and their influence on central and decentralized air conditioning systems.
Can I answer this question? Thank you, Liang. He's my old friend many years. And the natural ventilation is the first priority. I always believe very important. Open windows to let the air go through. Whatever central air conditioning or decentralized, the natural ventilation is very important in many cases. And but then sometimes the natural ventilation doesn't work with the mechanical system. So then if for centralized things, if I need natural ventilation, I just switch off the mechanic one, and I got my windows, I got natural ventilation. But for the central air conditioning system, the manager of that always say, okay, never open the windows. You will already be well conditioned your space. You cannot interrupt my system, you see. So from the point of the encourage the natural ventilation, then the decentralized system may be the priority. That's my point. Thank you.
Yang, maybe I will just respond to that question as well. So I think one of the fundamental things that need to be looked at when we are trying to incorporate natural ventilation strategy is whether the building is going to be air conditioned or the building is going to be running in a hybrid mode. Part of the time it is going to run just on natural ventilation, part of the time it is going to run on air conditioning system, or I think the building is only running on natural ventilation. And the strategies, I think, as Alexis also mentioned, that the building envelope, the way you design that, and that means that what is your insulation, what is your shading strategy, what is your natural ventilation strategy, what kind of bioclimatic designs that you design around your building becomes very, very important. So in my opinion, I want to use this lean, mean, and green construct. Lean is like you design the building so that you minimize the load that is coming on the building. And that's, I think, can be done through natural ventilation big time. Mean is when you go for the most energy efficient system to meet the load. And green is like when you use renewable energy or when you use natural or green refrigerants to start to meet your cooling demand. So I think that's how I see natural ventilation playing into, I think, how should you have an integrated building design approach. Thank you.
Thank you, Yi and Satish. I think that given that we have last 5 minutes, I'd like to read question 2, which we received. A few of the questions are based on the same theme. It's on the current situation on COVID-19. So the question is, given the situation about COVID-19, how should we design air conditioning and ventilations to mitigate the transmission?
Okay.
Maybe I think I will just very quickly intervene here. I know that ASHRAE has a pretty big focus right now on designing buildings, I think, and running the HVAC system in a COVID-19 situation. So there will be, I think, a lot of very useful and detailed material that is there. One of the things that we are seeing in India is that a lot of people, in order to save energy, are doing recycling of ventilation. And I think that's one thing that should be a clear no-no in a COVID-19 type situation, because the more recycled air that you are going to use, the chances of, I think, airborne transmission is going to increase. But clearly, I mean, it's a pretty big topic. There is a lot of, I think, good materials that is out there by ASHRAE and other organizations that people can look up to.
Thank you. One thing maybe I would like to mention that even for, of course, natural ventilation is very good for against this kind of works. However, even for the circulated air, as soon as you have the filter, not very high efficiency, say 60% or 70% of the efficiency filter, like the middle level F, I think this is in the United States also have this kind of level, normal filter. You put this, then they can take half of the particles that support this have some words on that. Then you can reduce the particles in the room that with the words. Because the air, first, the outdoor air is clearly no problem. Secondly, as soon as you take the filter to collect some words, particles, then the space you conditioned, the words is getting smaller. So then the major important thing, very important thing, is large amount of air, whatever circulated or come from outdoor, come from windows. the large amount of air is most important. According to our study recently, we learned, suppose there is one people, single people that do have this virus, then and other people want to stay in the same space for, say, 4 hours, then you need something like 3,000 cubic meters air per hour. They can make the dangerous, the probability to be infected down to less than 1%, something like that. They can make analysis of that. So large amount of wind is very important. The effective wind equal to the real circulation air volume multiplied by the efficiency. If the filter is say 60%, means the circulated air multiplied by the 60%, the result equal to the natural ventilation, because the same amount of air come from outdoor. It's the same functions. In this case, it's the similar functions. Thank you.
Thank you. Thank you, Yi, again. Thank you for all the panelists. I think that it is probably time for we to conclude, even though we do not have more time to answer every questions of the audience, but we have all the Q&A and we will try to respond them after this session. So now I would like to share my screen again because we have 2 more quizzes, 2 more poll questions for you guys at the end of this session. And so I'm going to launch last 2 questions. And so question number 3, if you can see it popping up on your screen, is sorry, this, yes. So question number 3 is, what in your opinion should be the focus of research and development community to sustainably cool people without warming the planet? So the first choice is cool the people, not buildings. And the second is develop the ideal refrigerant molecules. And the third is that we design a non-vapor compression-based cooling system with significantly less climate impact. And the last one is design an AI-driven on-demand HVAC control system. So so I'm gonna leave it open for a few more seconds, and then show you the result. So I am going to I'm going to end the poll right now, and if you can see the result, you will see that we have a we have lots of different opinions, right? So a lot of people voted for local cooling, cool the people, and some of you also voted design a non-vapor compression-based cooling system, also in addition to AI-driven. So it seems like we have a lot of focus of the future research, which is great. So the last poll would be that in your opinion, what is the most important area for research and development innovation in designing next generation thermal comfort solutions? And so we also have a few choices, and I would like to mention that this is really an opportunity to gain your feedback. So if you would like to offer any answer that's not listed here, please feel free to type them in the Q&A. And so the choices we offered here are hybrid design to meet latent and sensible cooling load. And obviously it's really important because we have to control temperature and also humidity. The second choice is that enhance the efficiency of heat exchangers, in addition to radiated cooling system and phase change materials for the thermal storage. So feel free to please type in your own understanding, your own thoughts in the Q&A session. So I am going to, we have a lot of responses, so I'm going to show you the result. So about half of the audience voted for a hybrid design to meet the latent and sensible cooling load. So this is our all we wanted to discuss and wanted to bring in some discussion within the community. So I'm going to stop sharing, and I would like to quickly just mention that feel free to submit any comment to the Q&A. And before we conclude today's session, I would like to thank our speaker again and thank all the panelists. It's really inspiring discussion and really inspiring talk and a lot of great discussions. Our next lecture would be offered by Professor Ken Goodson from Stanford University. So his talk will be not next week, but on June 3rd. And his topic will be getting the heat out, electronics cooling from smartphones to data centers. So more on the thermal management of electronic. So if you, we welcome to still participate in our next colloquium. And so with that, we will probably—
So I just want to take a chance to also thank Yang for doing a great job in moderating the session. So it's and so thank you Yang for nicely navigating through all the tools in the Zoom and nicely doing the polling. So again, thanks on behalf of the panel, I guess.
Thank you, Professor. Professor Prasher, for sharing your opinions, and thank you all the panelists, and thank you all the audience for your questions. And really thank Professor Gang Chen and all the student helpers for organizing this event. And we hope to see you in next lecture. And I think that we will leave the webinar open for a few more minutes for you to type in your questions. Thank you.
Thank you.
Thank you.